Today we're going to be talking about how to solve an initial value problem using Laplace transforms. And in this particular problem we've been given this second degree function 2y double prime, or the second derivative of y, plus 3y prime, or the first derivative of y, minus 2y is equal to t e to the negative 2t. We've also been given two initial conditions, y of 0 equals 0 and y prime of 0 equal to negative 2. Then I've gone ahead and written down 5 formulas that we're going to need from, and I've gotten these from a table of Laplace transforms. We're going to use the first 3 here on the left, f double prime of t, f prime of t, and this t to the n, e to the at. We're going to use these first 3 to plug into our original function, transform it, and then we're going to use the second 2 over here on the right when we perform the inverse Laplace transform to solve for the function f of t. So pretty self-explanatory here, at least in the beginning. We're going to take this formula here, f double prime of t, and we're going to be plugging in the right side of that formula in place of y double prime. Then we're going to take what's on the right side of this f prime of t formula, and we're going to plug it in for y prime. And then we're also going to make a substitution for y, but we don't need a formula for it. Then finally, we're going to plug in what's on the right side of this third formula here for what we have over here on the right side. That was messy. What we have over here on the right side of our original function. So let's go ahead and make these substitutions here. We'll start on the left-hand side, so we're going to grab here first the 2. We're going to do 2 times. Now remember, we're plugging in this right side of this equation here for y double prime. So we'll say s squared, and since our original function is in terms of y's instead of f's, remember that f of s denotes the Laplace transform, but since our function is in terms of y instead of f, we'll go ahead and use y in place of in place of f. So we'll say capital Y of s instead of capital F of s. So s squared times y of s minus s times y of 0, and again lowercase y because we've switched to lowercase f, minus y prime of 0. Now notice here we have y of 0 and y prime of 0. We're going to be able to use our initial conditions here in a second to plug in these values 0 and negative 2 for those things, but we'll get to that in a second. So now we've got plus 3, right, from my original function, plus 3, times what we've got here in our second formula. So s times capital Y of s minus y of 0. And then finally minus 2 times, and when we plug in here for y, we're just going to do capital Y of s. Alright, so we've made all our substitutions on the left-hand side. Now on the right-hand side, we're going to use this formula that we boxed here in teal, and we're going to change this format into the format here on the right-hand side. So notice that in the numerator over here on the right, we've got n factorial, so we're going to be looking at n here. Well, in our case, that's equal to 1, right? We have t to the first power, so we're going to have 1 factorial in our numerator, and then in our denominator we're going to have s, remember the s variable always stays, minus a. And you can see here a is the constant that is the coefficient on this t variable in the exponent. So in our case a is negative 2. So since we have s minus a in our formula, we'll have s minus negative 2, which is just going to give us s plus 2. And then that's all raised to the power n plus 1. Well, we already know that n is equal to 1, so we'll have 1 plus 1, which is 2, and so that's going to be squared. 1 factorial, remember, is just 1, so let me go ahead and just change this to 1 right now. Okay, so now we've made all of our substitutions, and we won't need these 3 formulas over here on the left anymore. What we're going to do at this point is use our initial conditions, y of 0 equals 0 and y prime of 0 equals negative 2, and we're going to plug in for these things here. We can make those, and then we're going to solve for capital Y of s, and that'll give us our Laplace transform. So we'll also kind of distribute these these coefficients here, the 2, the 3, and the -2. So let's call this first 2s squared times capital Y of s minus 2s times y of 0, we know to be 0, right? We have that there. So we'll plug in a 0, minus y prime of 0, which we know to be -2. So we have minus a -2, which is going to give us plus 2, but remember, we're multiplying by the 2 out in front, so it's actually going to be a plus 4. Moving on to our second term, we'll say plus 3s capital Y of s minus 3 times y of 0, which we know to be equal to 0. Then we'll have minus 2 times capital Y of s, and we'll go ahead and leave the right side as it is, 1 over the quantity s plus 2 squared. So now we'll simplify and solve for capital Y of s. This term here, let's get rid of these. This is multiplied by 0, so that's going to go away. This is 3 times 0, so that's going to go away. And if we now collect like terms, we'll have 2s squared y of s. Sorry, again that got a little messy. Y of s plus 3s y of s minus 2 times y of s, and then we have plus 4 equal to 1 over the quantity s plus 2 squared. So now we can factor out, let's first actually move this 4 to the right hand side. We'll subtract 4 from both sides. So I'm going to get a -4 over there, and let me just erase this. So we've got equals. Now we'll go ahead and factor out a capital Y of s, because we have it in each term, so we can easily do that. And now we're multiplying by 2s squared plus 3s minus 2 equal to, let's go ahead and get a common denominator over here on the right hand side. So to do that, we'll multiply the 4 by s plus 2 squared over s plus 2 squared. S plus 2 squared. And when we combine fractions, we'll just get 1 minus, let's go ahead and erase this, 1 minus 4 times the quantity s plus 2 squared all over the quantity s plus 2 squared. Now we can, and let's just go ahead, let's actually start multiplying out the top. So we'll have 4 times the quantity s squared plus 4s plus 4 all over s plus 2 squared, the quantity s plus 2 squared. And now we're going to divide both sides by this quantity here, 2s squared plus 3s minus 2, in order to solve for y of s. Dividing the fraction on the right by this quantity over here from the left is the same as multiplying by 1 over that quantity. So we're going to have actually 1 minus 4s squared, and this is going to be a minus here, minus 16s minus 16 all over the quantity s plus 2 squared. And bringing that quantity over from the left hand side, we're going to have this multiplied by 1 over 2s squared plus 3s minus 2. And now since they're multiplied, we can just combine fractions, and we'll get y of s equal to, and let's go ahead and consolidate here. So we've got negative 4s squared minus 16s, and then 1 minus 16 gives us a negative 15 all over the quantity s plus 2 squared. And we can factor this 2s squared plus 3s minus 2. If we do that, we'll get 2s times s, and we'll say plus 2 minus 1 gives us a 2s squared plus 4s minus s plus 3s minus 2. Yep. So we'll say times 2s minus 1 times s plus 2. And if you can see here, we've got s plus 2 squared and an s plus 2. So let's actually just go ahead and change this to s plus 2 cubed. And we can get rid of this s plus 2 to the first power here. So now, in order to go ahead and solve this, to solve the initial value problem, we need to perform a partial fractions decomposition on this y of s function, or the function on which we've already performed our Laplace transform. So we've gone from our original function, we've done a Laplace transform, and here we stand. Now we need to use a partial fractions decomposition to solve this. So in order to do the partial fractions decomposition, remember that we'll break apart the denominator here, and because we have a repeated linear factor here in the quantity s plus 2 cubed, remember that we'll have to include all factors of lower degree. This 2s minus 1 is also a linear factor, but it's a distinct linear factor. So that means that our partial fractions decomposition is going to look like this. We'll call it a over, let's do the 2s minus 1 first. So we'll do 2s minus 1. Then we'll have plus b, and remember we just need these variables a, b, c, d, as opposed to ax plus b or something like that, because we're dealing with linear factors instead of quadratic factors. So b over s plus 2 plus c over the quantity s plus 2 squared plus d over the quantity s plus 2 cubed. And remember that all three of these factors here for b, c, and d are included because we have this repeated linear factor of the quantity s plus 2 cubed, and because it's cubed we have to include s plus 2 squared and s plus 2 to the first power in our partial fractions decomposition. So because this is a Laplace transforms problem, I won't take the time to do all of the steps of this partial fractions decomposition, but let's just say that when we solve it for our coefficients a, b, c, and d, we'll get a equals negative 192 over 125. We'll find that b is equal to 96 over 125. C is equal to negative 2 over 25, but for the sake of putting all of these over 125, because it's going to make it easier on us, we'll get negative 10 over 125. And then here for D, we'll get negative 1/5, which we'll call negative 25 over 125. And you'll see in a second why it's easier to have them all over 125. So now, instead of this crazy fraction here for y of s, we'll go ahead and plug in instead our partial fractions decomposition. And we're going to pull out a 1 over 125 outside of our decomposition. And now we'll just go ahead and plug in the numerators of all of these fractions, so negative 192, positive 96, etc. So we'll get negative 192 over 2s minus 1 plus 96 over s plus 2. C is a negative 10, so we'll get negative 10 or minus 10 over s plus 2 squared, and then D was a negative 25, so minus 25 over the quantity s plus 2 cubed. Now this is where our fourth and fifth formulas come into play. We have this formula here for 1 over s minus a equal to e to the at. We're going to be using that for the first two terms here, the first two fractions in our partial fractions decomposition. And then we have the second formula here for n factorial over the quantity s minus a raised to the n plus 1. We're going to be using that formula for these two. And basically we're going to be performing the inverse Laplace transform. That's the final step that we need to do in order to solve for the function y of t, and therefore have solved our initial value problem. So in order to do that, we need to make each of these fractions into the same format as the formulas were given. So let's focus on the first two with this formula here for 1 over s minus a. So as you can see, 1 over 125 Essentially, if we factored out this negative 192, and in the denominator here, if we factored out a 2, right, then that would be multiplied by 1 over, the 2 is factored out in the denominator, so we're actually going to get s minus 1/2. Now this 1 over s minus 1/2 is in the same form as our formula, 1 over s minus a, so we can easily convert it to e to the at. So that's what we're going to do with the 96 over s plus 2 as well. We'll factor out the 96, and what we'll be left with is 1 over, and we could leave it as s plus 2, but let's go ahead and say s minus a negative 2, which is the same thing, so we have it in exactly the same format as 1 over s minus a. So those are our first two terms, and we'll perform the inverse Laplace transforms in a second. The second two terms here, we need to get into the same format as our second formula, and again, these formulas are from our table of Laplace transforms. So in order to do that, keep in mind that first we need to have this s minus a, so we'll do that. But then the exponent here, n plus 1, we need to figure out what n is in this n plus 1 exponent and then make sure that our numerator matches that for this n factorial. So we're going to pull out a 10, right? We're going to pull that 10 out. We're going to say minus 10 times, we'll leave the numerator for now. We can see we have s plus 2 here, so we're going to say s minus a negative 2 to get into the same form. And then notice that our exponent here is squared, which is 1 plus 1. So if we have 1 plus 1, then we know that n is equal to 1. So we'll go ahead and say that we have 1 factorial in the numerator, which is just 1, and that's fine. So we have 1 over the quantity s minus negative 2 squared. Then for our fourth term, we'll do a similar thing. We'll pull out the negative 25. Then we've got this multiplied by, in the denominator, we'll have again s minus a negative 2. Then the exponent here, we have a 3, which essentially is 2 plus 1, right? If we're looking at the exponent here, n plus 1, if our exponent is equal to 3, then n has to be equal to 2. So we'll leave this as a 3, but we need to, in the numerator, say 2 factorial over 2 factorial, because we know from the n plus 1 exponent in the denominator that n is equal to 2, so we need to make the numerator n factorial, and the only way we can do that is by saying, multiplying by 2 factorial over 2 factorial, and now we can pull out a 2 factorial. We'll pull out the bottom one here, so we'll just be left with 2 factorial over this denominator. So now that we've converted everything into the same format as our formulas, we can go ahead and perform the last step of our problem, which is the inverse Laplace transform. So let's go ahead and do that up here. What we'll get is y of t, which is going to be equal to 1 over 125, that'll stay out in front. The negative 192 over 2 is going to be negative 96. And our formula tells us that this part here, that we've set up 1 over s minus 1/2 in the same format as this formula here, 1 over s minus a, it tells us that a is equal to 1/2. So we're going to convert that 1 over s minus 1/2 to e to the 1/2 t. So we'll get e to the 1/2 times t. Then similarly, we're going to have plus 96 times e to the negative 2t. Then our second formula, we're going to have minus 10, and notice that we're converting it into something that looks like this. So minus 10 times t, so we have t to the first power, which is just t, and then multiplied by e to the at. Well, we know that a is negative 2, so we have e to the negative 2t. And then for our last fraction, we'll have minus 25 over 2, and again here multiplied by t raised to the n power. Well, we know that n is equal to 2 because we have 2 factorial in the numerator, and because our exponent here in the denominator is equal to 3, and we know that n plus 1 has to equal 3, which means n has to equal 2. So we have t squared and then e to the at, where we know a to be -2. So we have e to the -2t. And that's it. That's our final answer. So again, we used our formulas here from the table of Laplace transforms to perform the Laplace transform on our original function. We plugged in our initial conditions. Then we had to use partial fractions decomposition to get our function to the point where we could perform an inverse Laplace transform. And once we perform our inverse Laplace transform, we get a function y of t, which gives us our final answer. So that's it. I hope this video helped you guys, and I will see you in the next one.